This report discusses a comparative analysis of models for assessing the severity of bronchial asthma in children based on paraclinical data. Bronchial asthma holds a specific place among allergic diseases. Currently, due to the rapid increase of asthma incidence, this pathology can be considered as a global medical problem. There is a fairly large category of patients who are characterized by an uncontrolled or severe cause of the disease, which confirms the presence of different pathogenetic mechanisms of the onset of bronchial asthma. For a comparative analysis of the model, we will use the result of clinical study of the severity of bronchial asthma in children in the Kharkiv region in 2017. The asthma severity analysis group included 90 children aged 6 to 18 years. The structure of the group was as follows. The main subgroup included 70 children with bronchial asthma. The control group, 20 healthy children. Analyze the data of a survey of parents about the symptoms in patients, characteristic of bronchial asthma, as well as the history of the disease of the patients. This information served as the basis for the values of the qualitative factors used to build the regression model. The clinical features of the cause of the disease have been studied. Based on the results of laboratory studies, the value of the quantitative factors of the model were formed. During the analysis, 142 factors were considered. The main biomarker studied in the work is thymic stromal lymphopoietin, a cytokine that plays a key role in the pathogenesis of allergic diseases, including asthma. In constructing the forecasting models, mathematical statistic methods based on neural networks were used. These methods are a tool for constructing dependencies between the severity of asthma and A. The value of the TSLP and the severity of bronchial asthma. B. The values of factors based on clinical blood test. A comparative analysis of the forecasting results using two types of dependencies will allow us to assess the accuracy of the forecast. The numerical statistical characteristic of the input set of model factors and observed values are given in the table. The output parameters of the model are the severity of bronchial asthma: severe persistent, moderate persistent, mild persistent, intermittent. The calculated correlation coefficients between the model factors as well as between the model factors and the observed value are also presented in the table. A multi-layer perceptron was used to create each of the two models described above for predicting the severity of bronchial asthma in children. The neural network architecture contains several layers, each of which is connected both to the previous layer, from which it receives data, and to the next layer, which it influences. When calculating the observed values, the same network architecture was used for the hidden and output layers in each of the models, each node of which has the same activation function for two models. The neural network architecture for Model 1 and Model 2 is shown in Figure 1, Figure 2, respectively. The architecture of the models differs in the number of neurons in the input layer. The neural network training process for the TSLP model is shown in slide 7. To demonstrate the neural network training process, 4 samples with the maximum accuracy value were selected, containing the two above-mentioned datasets. The maximum accuracy value is 0.67 for the TSLP model training process. For comparative analysis, the neural network training process for the TSLP model is shown on slide 8. As for the TSLP model, the CBT model shows a maximum accuracy value of 0.67 for the training process, equal to the value obtained for the TSLP model. One difference is that for a given number of epochs, for each of the model, 20,000 epochs max, loss accuracy and test loss function asymptotically tend to the value determined by the model parameters, while the learning process for the CBT model neural network is not steady state. The comparative analysis shows that the CBT model, which incorporates multiple clinical factors, is not inferior in predicting the quality of the TSLP model based solely on the TSLP level. Although TSLP is an important biomarker associated with asthma severity, it does not encompass the entire multifactorial nature of the disease. The sufficiency high accuracy of the CBT model indicates that the integration of multiple clinical indicators provides a more complete picture of disease severity. So, the conclusion. Two developed models, one based on thymic stromal lymphopoietin (TSLP) levels and the other on clinical blood test factors, provided a clear picture of the correlation between the model regressors and the severity of asthma. A clinical blood test-based model showed significant predictive accuracy, offering an alternative method for assessing disease severity. The results highlight the importance of developing cost-effective and accessible diagnostic tools tailored to the specific needs of resource-limited regions. Thank you for the attention.